Hi, welcome to an Arduino tutorial from Robojax. In this video I'm going to introduce this DFRobot Power Shield. I'm going to explain all the input, outputs and all the features of this. Then I'm going to have a look at that. Then I'm going to look at the data sheet and see the specification of this regulator that is used. After that we are going to see the schematic diagram for this shield. Then I'm going to show you the example code that you can control this, turn this off and on using Arduino. Also, we're going to see how we can use the voltage, the V sensor of this. So take some action based on the output voltage. We're going to see how to control a motor, turn it on and off, and also at the end I'm going to test the current load at the output stage at different voltages to see how much current it can supply to the load. So at the end, I'm going to show you how you can use LCD1602 as a voltmeter to display the voltage of this module. You can get the code for this by clicking at the link in the description, which is below the video, which will take you to robojax.com/learn/Arduino. Let's get started with this. This is a DFRobot shield. Oh, it's called shield because you can attach it directly on Arduino. It will be inserted here, and all the pins of Arduino will be available. Nothing will be used or consumed except one of the pins that is used for the device, pin 13, for turning this on and off. And also we have another pin, analog 0, if you want to read it or sense the voltage using Arduino. Other than that, your all pins from Arduino are available here. In this side we have the input power. It has labeled here very tiny with pluses on this side, minuses at this side. You can put up to 35 volts as an input here. And then this is the output you can get. According to the data sheet, about 12 volts, but I tested it. I was able to get 14 volts as an output. Output can be adjusted using this multi-turn potentiometer. Here we have some LEDs. The first LED is when the device is off, it will show you that the device is off. This light will turn on. When this is off, this device is working. And then we have a voltage level indicator of 3.35, 9 and 12 volts. They will turn on from here slowly. When the voltage maximum reach, all of the lights will be on. Then we have two jumper here. This jumper is if you want to control this using the pin 13, you must put this connected. Otherwise, remove this and the pin 13 will be free for you. This is connected to analog 0. If you want to detect the voltage, leave this jumper here and you will be able to use internally, just set the code to read analog 0 and you will have the voltage. Otherwise, just remove it. This will be disconnected from analog 0. Here we have jumpers. Sometimes you want to use only the 5 volts and then use the regulator to get 3 volts or lower voltages. Then you can move this jumpers on this side. Let me remove it. So both wires, we have 2 of those. Now if I remove it, now the output will be disconnected. When you put this, actually you're connecting the between these two, you're connecting the voltage from outside. So you must put it on this side. If you put it, other than that, there is nothing. So we have a Schottky diode here for overload and overcurrent protection. And also we have this op amp that converts the voltage and to display this for us. And the output voltage, because it goes up to 12 volts, it has been scaled using 2 resistors here, which I'm going to explain next. Why we use this shield at all? The first thing is you will eliminate a lot of wiring, so you will have only one power and everything will be contained here, and you can focus on your other elements or pieces that you're connecting on top of this. So this eliminates a lot of wiring, plus you will have a regulated voltage. You can adjust it. Whatever is your voltage, input voltage, you will get 1 volts below that, regulated. So let's say you put 15 volts here, you can get between 1.2 up to 14 volts here as an output. So this also can be used as a to control the motor, and you can control 3.3 motor, actuator, servo, or whatever they need if they need a lot of current, because this can supply higher current than Arduino, and Arduino is very minimal power. So this is a very good tool to eliminate all those wiring and also provide higher power for your devices. The width of the module is 56 millimeter, 55.9. The length is 57.4 millimeter. The depth is 12.6 millimeter. We have here the Schottky diode SS54, which can handle up to 5 ampere. So this will act as a polarity protection and freewheeling as an output stage in case if you have an inductive load, so you don't have to connect another diode as an output. And as you can see, the cathode is connected to the positive, and the anode is connected to this negative. So you don't need to put extra diode for inductive load. This is the schematic diagram for this power shield. This is power in. As you can see, this is connected to this is the input, and this is the power out. The output goes to the output from those two pins. The in ground is connected, and then this has been connected. This goes here, that's a VN. The voltage is adjusted using this potentiometer in series with this resistor that's connected to the output. So this is the reference feedback. So this is the potentiometer that you're rotating. Normally, if you want to control this on and off, if you connect this jumper to pin D13, if you do not put this jumper, it will always be output will be always on. You don't need to connect it. So this is a pin that you can control the output on and off accordingly if you need it sometimes. Then here we have an op amp LM324. This is 4-piece op amp, and the output voltage have been connected through this non-inverting input with reference voltage of 3.3 volts at the negative, and then the output is connected through this LEDs. The input voltage for each have been scaled with this resistor. As you can see, 1 kilo ohm 5, 20 kilo ohm 4.7 with these dividers. So this will reflect the output voltage. These are approximate because this is analog, and also the value of these resistors have 10%, maybe less or more accuracy. So this gives you approximate output voltage indication. Then D13 is also connected through this 1 kilo ohm, and we call it L. Let's have a look at the data sheet. This is a power shield for this power module. As you can see, it can give you 1.25 up to 12 volts, 3 ampere peak, and this is the supply voltage and output current 2 ampere. It says efficiency is, and here are the pinout. Now let's have a look at the data sheet. The regulator that is used on the power module is LM2596 from Texas Instrument. It has a back converter with a frequency of 150 kilohertz, which are not of our concern. We are concerned with the current. The rated current is 3 ampere. The output regulated voltage is 1.2 to 37 volts, but on this device it has been limited to about 14 volts. And the load current is 3 ampere, but suggested load current from the manufacturer of the module is 2 ampere. The typical standby current is 80 microampere. This is one of the typical application. It has 5 pin. Pin 1 is the input and pin 2 is the output. Here pin 5 is used for on and off, and when it is on, you have to set it at low or below 1.3 volts, which is low. It will turn on, and if you want to turn it off, this should be connected to higher voltage. It will be turned off. And the rest of the information are for the design, but I will provide you the link, so if you want to have a look at it. Now let's have a look at the code that I've written for this. Now I've set this pin 13 as an output, and then we set the pin 13 low, so initially it will be on, and also then we set the serial monitor to be turned on. If you are just turning this on and never touching it, this must be here. Otherwise, if you're playing with it and turning it on and off according to some action, then you can remove that and this will work. So we are turning the power system on. So we are turning the power module on and then wait for 3 seconds and then turning it off. Because this is a loop, it will come back, wait for 4 seconds off and then turning it on, and then wait for 3 seconds and continue. So this is just a demonstration on how to turn this on and off. Now I have connected the motor here and the voltage is around 4 volts, just like that. And also we are printing the text on the screen. As you can see, when it says off, the light is on. When it is on, the light is off. So be careful and pay attention. Now I'm connecting the power. Now the power is connected, it's off. So the output is on, as you can see. Now it's off, so pay attention to that. Now it's on and this is running and the voltage is also showing. So Arduino is turning this on and off for us. Now I've connected this huge motor, but this can draw only 1.2 ampere at 12 volts. So the current will be very low, but even at 12 volts this device can handle it, so the power can handle it and no problem. So that is off, and as you can see the light is on. So now it's on and we can see it's off, the motor is off, and when it's on, the motor is on.
He's back and welcome.
Now I have increased the voltage. As you can see, the number of... Keep in mind that this cannot be used to control the motor and change the direction. It's just turning it on or turning it off at any voltage that you set. Now I've connected the input. As you can see, it's 22 volts. The input will be connected here. The output will be connected to this port. Now I've connected to my voltmeter here, and I can adjust my input from my power supply to show you that I can go up to 35 volts or at 30 volts here. So this can accept up to 35. Doesn't matter because the output is independent of input. As long as the output is lower than the input by margin of about 3 volts, it will work fine. So let's just test it. So this is 1.1 volt. Let's change the output voltage. To change the output voltage, if I go to the left, that's the minimum that I can get. I'm going clockwise rotation. Now as you can see, we are reading 1.3 volts, 1.7, it's very precise, 2 volts. So this bar graph also shows approximate voltage here. It shows 3.3, light is on, but we have 3.7, but the light will go as the voltage gradually increase. So it goes to 5, 9 and 12 volts. So now we are at 5 volts. Six, 7. Now we are almost 9. So this is 9 volts at the output. It's 10 volts. So I'm just going maximum. It shows around 13 point. So 14 volts it shows. But I realize that the output can change with the input. For example, if I go below certain voltage, this will drop. So 14 up to 22. So it's very stable with respect to input, because even if I go 30 volts, it's 14. Now I'm going back. 18 volts. We are still getting 14 volts. Let's see. So now at 15.5 we are getting 14 volts. At 14.7 we are getting 14 volts. That's 14. Now it dropped. So you should have at least 1 volt higher than the output. So if you want 6 volts, you must have 7 in order to get 6, or any other voltage that you want. According to this data sheet here, you can, if you put this jumper together, this will be connected to analog 0. The output voltage will be sent to analog 0. And now, because this input of analog can accept up to 5 volts, they have scaled the output voltage through 2 resistors here, so it is always below 5 volts. The output voltage from here, this is the output from this regulator, LM2596S, adjustable. So this is the output which is connected to these 4 LEDs to show you the voltage level at 3.59 and 3.359 and 12 volts. But from this voltage also we have connected it here through this it has been connected through this 30 kilo ohm and then 7.5 kilo ohm in series to scale it down, because it goes through this jumper to analog 0. So when you put the jumper, the voltage will be connected, but because input voltage can accept only up to 5 volts maximum, so we have to divide this through this voltage divider. So keep these values in mind so we can read continuously the output voltage. This is continuity to start. I've connected it to analog 0. Analog 0 is connected here to this. If you put this jumper, then this can act as a voltage sensing, so the voltage can go in and you can read it as a pin analog 0. Read the output voltage, we have to create a factor understanding those resistors. So we have 30,000 ohm or 30 kilo ohm resistor plus 7.5 kilo ohm, 7,500. So this is 37,500 divided by 7,500. This is just voltage divider calculation, and the result will give you 5. So that's a factor. I put it as a factor as float. The rest of the code is not changed, so we are reading the analog 0. The value will be stored as an integer, as a raw value. Then we have to calculate it, so we get raw value 5 divided by 1023. This is 1023 step at the analog 0 input, so we have to get that factor multiplied by this raw value, and then we have our own voltage divider factor that I mentioned here, the 30,000 and 35,000, so that is 37,500. So this, when we can multiply everything, which will give us actual voltage, and then we are just printing it with 3 decimal place on the serial monitor. Here is the serial monitor. Now I've connected the input voltage here, and we have around 18 volts, but our concern is the output. So I've connected this through this voltmeter. As you can see, it shows 9.04 and fluctuates 8.9 something, so this is 9 volts. Now let's adjust the voltage and see if we are reading proper correct value. So I'm reducing it. Now we are reading 8.3 and we are reading 8.2, 8.3, 8.26. So that's correct. Let's go up. Maximum. So we have 13.9 and here 13.83 or 13.9 as it fluctuates. Let's go low, the minimum. Now we are reading 1.2 volts at the output, and here is 1.17 or 1.19. So this is very close, but as I mentioned, there is some accuracy issue, but it's pretty close to the value that you're reading. Now you want to you want to control this device if the voltage, let's say, goes above 11.5 volts. So that voltage you can set, if voltage is above 11.5 volts, you can set pin 11 to high. High means turn it off, and also parenthesis text saying that voltage limit reached. And then we wait for 5 seconds, whatever you want to wait, or you do something else. Whatever you want, you can do between these parentheses. So do your action when the voltage is above 11.5, and otherwise just set it back to low, and then the loop continues like that. Now let me change the voltage and reach it, make it above 11.5 volts. So I'm rotating it counterclockwise, and you can read the voltage here. So up to 11. So now we are at 10. Pay attention here. When it reaches 11.5, it should have shut off for 5 seconds. And pay attention to this light. This light will indicate the state of this device. When this is off, the device is working. When the device is off, this will go high. So 10. Now I'm going. We are 10.8, 11, now 11.1. So as soon as we reach 11.5, it says limit reached, and then the output is off, and you can see we are getting 5 seconds and it goes back. So this can be used as a preventive mechanism. If something goes wrong, you can shut it off and do something, or maybe do whatever you want. Now the input is 20 volts. I'm not going to touch the input. Our concern is with the output, which is 12 volts, and this shows the amount of current that draws internally, and this is the load current. From here, this is the amount of current that it draws, so this is of our concern. Now I've set it at 3 ampere, and let me turn it on. So as you can see, the load is drawing 3 ampere, as if it's 3.9 ohm and 11.7 volts. So the voltage has dropped, and as you can see here, the input current is 1.89 ampere. So it consumes 1.89 at 20 volts, which is 38.3 watt. If you consider this as 12, so you can calculate also the efficiency. I'm now touching now this is getting hot, very hot, and it seems, I don't believe it can. So yeah, internal protection might kick in because the voltage dropped. As you can see, its internal protection is shutting it off because it heat up. Now with the 2 amp, it draws now 1.28 ampere. So this cannot handle 2 ampere continuously. As it heats up, the system shuts down. So let's go for 1 amp. 1 ampere is very stable, but so now we have 1 amp, 12 volts, very stable. Let me go here, 1.5. Now this is at 1.5 and 12 volts. And if this goes off, you will see also the current will drop because the internal protection will 2 ampere at the input, 1.27, 2.8, and we are getting 1.5 at 12 volts as the output. It seems tolerable. The output voltage is 9 volts. and it draws 0.85 ampere from the input, and the output is 1.5 ampere. Very normal hot, but not crazy hot. So let's increase the current. 1.6, 1.7 amp, 1.8 amp, heating up significantly. So you can get 1.5 amp at 9 volts as well. After running it for a longer period, I realized that it can handle only 1 ampere at 9 volts. Now we are at 15 volts input, 5 volts output, and it's 1 ampere. Now it's 1.5 ampere and 5 volts at the output. Let's see if it can handle it, and we are looking at these light and also check the voltage. If the voltage drops, it's overheating and it cannot handle it. So at 5 volts output we can get only 1.5 amp. Now I've connected it with 1 ampere, 3.3 volts, so 1.5 amp. Very normal, absolutely, I don't feel any heat. So 1.5 amp at 3.3 volts. I have separate video explaining this fully, so I'm not going to explain here, just give you the example on how this displays the text for you. I'll also give you this code that you can connect your LCD 1602 with the I2C module with a 4-wire only. This is very simple. So you can have your voltmeter, the output voltage will be displayed here. Only using these 4 wires will be occupied, 2 from VCC ground and 2 wires will be used for the A4 and A5 to connect this. And here is a code that it shows the voltage 11.7 as you can see. So I can change the voltage. Let me go lower. Also put for your reference this voltmeter so you can see both voltages. So that is off, and as you can see the light is on. So now it's on, and we can see it's off, the motor is off, and when it's on, the motor is on.